Hello, so today we are doing this problem called validate binary search tree. Let's just verify that the stream started. Okay, so it's starting. So the problem says that we have a binary tree and we want to determine if it's a binary search tree, basically. So that's the problem that we are faced with here. And so the problem says that a BST is when the left subtree of a node contains only nodes with keys less than the node, and the right subtree contains only keys that are greater. And so we want that, and also the left and the right subtrees should also be binary search trees. So for example, this node 5 should be less than its, the left should be less than it, and the right should be bigger, and also the subtree here should also be a BST. So that's the gist of the problem. So how can we solve this? So first let's take some example here. So the first thing we can think of is, so we have this tree that has 5 and then has 2 and then has 6 here, right? Now the first thing we need to check is that the value on the left side is less than the value on the right side, is less than the value of the node, and the value on the right side should be bigger. Now here at this point, a good question to ask the interviewer is, what do we do with duplicate values? Basically, what should we do if we have a tree like this, where the value is the same? So I'm just going to, since I don't have that interviewer right now, so I'm just going to assume that this is rejected, that this is not a binary search tree. So this is my assumption, yeah, in the interview, if the interviewer says a different assumption, then we can work with that. Okay. Now the other thing we need to do is so basically what I did here is, this one is the first thing they said, the constraint said, and the second one is this one, and then the last one that I need to verify is that both the left side and the right side are binary search trees. So I can just check. So I can just check that root.left is a binary search tree, and that root.right is also a binary search tree, right? So I need to check these two. What else can I do after that? So this is, does this solve the problem? So this is a good first solution, but there is a case that this doesn't handle. So what if I had 5, 2, and then instead of having 6 there, I had a 6 here? So this with my algorithm check here, with my check here, this would pass because 2 is less than 5, and then I go left to validate the left side, and then I find that 6, which is on the right side, is bigger than 2, and so all good. And for the root.right, since it's null, it's by definition good. And so this will return true. But if you look at this 6, it's on the left of 5, but it's bigger than 5. So it's not really a binary search tree. A binary search tree, anything on the left, whether it's on the right of the left child or not, it should be less than it. And anything on the right, whether it's a direct child or a child of a child, should still be bigger. Okay? So how can we solve this problem? So basically, essentially what we are doing for this case is that any value on the left, any value on the left side should be less than the root value, and any value on the, so that's the first thing, and any value on the right side should be bigger than the root value. That's what I'm saying here. And so basically what this means is that left values have max as the root, and right values have min as the root. Okay, so that's very clear. So basically, let me just show also the right side case. So the right side case is having 5 here, and then having 8 here, and then having 3 on here, right? So for this case, with this it will pass, but it's not a binary search tree because 3 is less than 5 and it's on its right. So basically anything on the right should be bigger than 5. So 5 is the minimum that any value on the right should get. Actually it's 5 plus 1 because they all should be bigger than 5. And so we know that the min of the right side is the root. Now what happens for something like this? So for 2, if we have a tree that has 2 here and then 6 here, like this. So for 6 we know that it has to be less than 5. The value here has to be less than 5. But since it's on the right of 2, it has to be bigger than 2. And so it's kind of should be between 2 and 6. So 6 should be, so the value at 6, let's call this node X, right? So the value at X should be between 2 and 5, which is basically means that it should be between its parent value, which is 2, and the root value, which is the max value that would pass. And the same thing with for the right, except for the right side we will replace we need reversing, because the value here at node Y, if this was Y, then we are expecting that value at Y to be between, so the value at X here, so the value at Y should be between between 8, should be between 5 and 8. Basically it's on the left of 8, so it should be smaller than it, and it's on the right of 5, so it should be bigger than 5, right? So it's in this interval, which means that it should be between the root value, which we said here that it's the min of anything on the right, right? So it's the min value and its parent value. And so now we have kind of a formula to handle this. And so what is that formula? So it's that the value at the node should be between some kind of min and max, so which are the values that we will pass here, the max and the min. So basically if our node val is bigger than max, the max value that we are going to pass, which for the left side will represent the root, or if that value is less than the min, and our min will represent the root value for the right side. In that case, we should just immediately return false, right? And after that, we need to just recurse on the left side and on the right side to find our solution, right? And so here we just make sure that it's in the interval that we want. So for the left side, the max would be the root value, the min would be the parent right away, which is what we said here, and for the right it's what we said here. And so after that we can just recurse and check and do this basically. But we just need to pass the values for min and max. So we said for the left side the value for min is, so for the value at X should be between 2 and 5, so it should be between its parent value and the root value. So its parent value, that's the root val, or let's call it just node. So that's node val. And for its and the root value, which is the max value. So we would have the max value here. And for the right side, it should be between the root value, which is the min value, and its parent value. So the root value is the min value, and its parent value is node.val, right? And so this is pretty much all we are going to do. So let's just copy that here. And so here we need to return false. And for this, we need to return that. And yeah, that should be one thing I said here is that if the values are equal, that we want to reject them. So let's just add an equal here so that we can reject equal values. And so that would be something like this and this. And yeah, so that should, we just need to name this function here. So basically, since the root function here gets BST, so I'm doing this. So I need just to name this node to make this simpler. And I need min and max, right? And so for the first case, I just need min to be the smallest value possible, because I will be comparing it to the root, and the root can be any integer. And so I just need that to be float of minus infinity, and my max needs to be any the biggest value possible, so that the root can be any value. And so I'm just going to say float inf like this, and as the default value. And basically, because Python min and max are functions, I'm just going to do v here as in value, so that this can run correctly. And so let's call this, let's call that, and this should pass. We have small issue here. So yeah, I'm missing this semicolon. It is valid. So it's saying that this is, maybe I wrote it wrong. Oh yeah, it's a class function, so it should be this. One thing also that I didn't handle is if the node is null, that we reach at the bottom, the node is null, then an empty tree is by definition a BST, so I should return true. And I'm checking if it's less or equal than the min, and then if it's bigger or equal than the max. Okay, so let's see here. We still have this one saying false, 2, 1, 3. Where are we making the mistake? Yep, so basically for the left side, we said it should be between the parent value and the so it should be between 2 and 5, but 2 is its minimum, and so this is the min. The min is the first parameter I'm passing here, and so basically I'm reversing these. So my min should be and then my max should be the parent. So the left side, the max value should be the root value, which is the node value, and then its minimum should be the previous minimum. And for the right, we should have node.val, and we should have vmax here. Yeah, so basically I messed up here a little bit, because the value at x should be between 2 and should be bigger than 2. It should be bigger than 2, and it should be smaller than 5. So its minimum should be the previous minimum, and its maximum that it can reach should be the parent, which is the parent value, which is the value. So, yeah, so x is on the right, right? So x is on the right, On the right side, the value should be between the node value and the max, which is 5, which is here. So basically this is a right side, and so I should apply this instead. So actually I should say y here and x. And for the x side, since it's on the left, should be between the root value, which is the min value, and the node value. That's the correct way of explaining this. Yeah, sorry about that. So we just need to swap these. I explained them in the wrong order. Yeah, but this should pass. Okay, so that passes. There is another way to solve this problem. Let's see it here. So we know that Inorder Traversal. So Inorder Traversal for a tree. So we know that an Inorder Traversal gives us a sorted sequence. So Inorder Traversal of a tree. Just to make sure that this is still recording. Okay, cool. So Inorder Traversal of a tree gives a sorted sequence, right? And so of a BST actually, because we know that for a BST the left side is smaller than the node value and the right side is bigger than the node value. So smaller the value and then bigger, which is the definition of a sorted sequence. And so we can just do the Inorder Traversal, get the sequence from Inorder Traversal, and then check if it's sorted. Then that means it's a BST. If it's not sorted, then it's not a BST. We just need to add one additional thing, which is handling duplicates, so that if we find the duplicates, we should say false. Since our definition here of a BST is that it should not have duplicate values. And so let's define our Inorder Traversal for our tree. And so that would be node and the list in which we are going to add the values. And so we need to call that here to get the result, which is the sorted sequence. And so root, and we start out with an empty list. And then we need to call Inorder Traversal on node.left. And also if like we reach at the end, we need to just return the list. And we need to do on the left side first, and then process the node itself. That's the definition of Inorder Traversal. So that would mean append node.val, and then we need to do Inorder Traversal on node.right list, and at the end we need to return list. And now we need to check that it's sorted, so and that there are no duplicates. And so we can just go through starting from 1 to the length of res and check if res, the previous value, is basically bigger or equal. That means that it's not sorted or there is a duplicate value. Then we can just return false at that point. If we reach the end and we didn't violate the condition here of a BST for our sorted sequence, then we can just return true. Okay, and so let's run this. Okay, so we have the root here called node, and I no longer need this min and max. Okay, so I think this should pass. Okay, so our solution here passed. Now you can see here that I'm first doing the Inorder Traversal and filling the entire list with values. What happens if we have a case that is like this? So we have the root 8, and then let's suppose 6, and then we have lots of values here. Like let's say it's really big tree after that. So here we could have failed already at the first test because 8 is bigger than 5 and it's on the left. But here we will continue until we finished everything and then do the list. And so how can we adapt this Inorder Traversal so that it can do this, but it doesn't have to go through the entire tree, and it can fail right away. And so the first thing I'm going to do is just do the iterative Inorder Traversal first, and then from there we can adapt it to use this. And so, because just doing it with the recursive one is a little bit complicated. And so the Inorder Traversal in the iterative way would be, so first we will check, let's call this a root. So first we will check our root. If there is no value, then we could just, at that point, we could just return true, because that by definition is a binary search tree. And then after that, for our Inorder Traversal, we are going to initialize a stack, and then we are going to say while stack, and while we have root value or something in the stack, at that point we are going to add all the left values, and then add the value, and then add the right side. That's the definition of Inorder Traversal, is process all the left side, and then the node, and then the right side. So that means that while root, we are going to say stack that append root.left, and then we are going to assign root.left so that we can go all the way left. Now once we went all the way left, we want to process the node, and so that would mean just pop the value, and so now we have the new root value, and then we want to process it. So process here, I will define that process step later. So this is basically the template of Inorder. We do the traversal, and at some point we process the node once we pop it from the stack. And then after that we are going to say root.right, and then let it go to here so that it processes all the left side of the right first, and then processes the right node. And after that we can, here at the end, we can return our value. Now what is the process step? So the process step, if we were to do the same thing we did earlier with the sorting, it would be a list, and we would just add append a root.value, right? And then at the end we can just sort and do the same thing I did earlier. But I wanted to do it in a way that as soon as we find a failure case, we can just return false. So instead of a list, I'm just going to keep track of the previous value and compare it with the current value, because that's all I'm interested in anyway. If I generated a sorted sequence, I would just check each element with the next one. So I can just do that while traversing. So the previous node is none, starts out as none, because the root has no previous node. And in the process step, instead of adding the element in the list, I will just check if I have a previous value, that the previous value is for sure, if it's bigger or equal than the current value, that means that it's not sorted or there are duplicates, right? So this is the case, then I can just exit right away, which is the case I have here with 8 and 5. Otherwise, I would need to make the prev value be the new root, be the root now, and then I can go right, and the right side will use this instead. And so if this condition never happened, that means that we have a BST, and so we can just return true. Okay. Yeah, we need to append the root first, and then go left. Okay. Okay, let's submit this and see if it passes. Okay, so this passes. So this is a good thing to get used to, is basically doing a traversal, an Inorder traversal on a tree. It's the exact same way that for an array we do a sequential traversal. And so here for a tree, for an array we do a sequential traversal, and then each time at a position we do some processing, right? So here it's almost the same thing. We do an Inorder traversal on the tree so that we can do some processing. So we have a lot of problems that we can apply this method to by just changing this process step, and everything else can be the same. And maybe we can not keep track of the previous value and keep track of something else, but the idea is that this is the template for how we are traversing the tree, and then we are doing something here and checking something or counting something. And yeah, that's all for this problem. See you next time. Bye.